recent thesis of Kate Perkins from Harvey Mudd has revealed a theorem of Leon Glass from 50 years ago, which is a discrete Poincare Hopf theorem, relating this to a theorem which I have proven. I was unaware of this theorem, and I want to give my own account on this. First of all, the proof of Leon's theorem, and then also the relation, maybe with a later version of the theorem I have shown in 2019. So first of all, the theorem of Glass deals with graphs which are embedded in a two-dimensional compact manifold. It doesn't have to be a sphere, it can be a donut, it can have higher genus, and the Euler characteristic is so for an oriented surface 2 minus 2g, where g is the genus. It should partition the space into faces which are polygons simply connected. And so this is part of topological graph theory. It's not intrinsic graph theory. We have to assume something about the embedding. And then we have the Euler characteristic is the number of vertices minus the number of edges plus the number of faces, which has a long history, this Euler characteristic. It's essentially the history of topology. It started in 1537 with Maurolico, and maybe just I ran out of space here, 1944 with Chern's Gauss-Bonnet theorem. So we have a long history, and it's very, very interesting kind of how this developed over a few hundred years. One can assign an index to the vertices and faces of the graph. And that's what Glass did. He assigned vertex 1 minus r half, where r it counts the number of changes of adjacent edges. So for example, for a vertex here, when we have a change, there's no change here, but there's a change here. We count that as 1. We count the number of changes. That's r. And also here, when I'm looking at the face, I'm looking at the number of changes. There's one change, there's no change here. There is a change, there is a change. So there are 4 changes here. So if you have 4 changes, this means it's 1 minus 4 half, it's minus 2. So this face has index minus 1. It's actually a saddle. It's essentially a saddle point here. So the case here is actually there's no change. If there is no change, like here, if you have a rotation with an elliptic point, it's kind of, so that would have index 1. Glass theorem has indices both for vertices and for faces. And now, if we are just keep track of all these sums, if you add this all up, so we have the ones produced here from the vertices produces the number of vertices, the ones from the faces produces the number of faces, and then we have just to realize that the 2 times the number of edges is the sum over all these r's. Now this is essentially kind of the Euler handshake formula, similar argument in the Euler handshake formula, not exactly, but you have just to realize that if you are going here and you have a change, if you have this edge here, so either you have a change at the next vertex or we have a change at the face. That's the key. So there's always a change. There's either a change in the face or a change in the vertex. So what happens here, this is no change in the vertex, right? They both point in, but there's a change in the face. So it's this duality which actually has been used. Van Stout was using duality heavily for proving the Euler polyhedral formula. So much of the history deals with 2 dimensions. This was also Poincare Hopf has first been proven in 2 dimensions, and then by Poincare, and then in higher dimensions by Hopf, and also Gauss-Bonnet has first been done in 2 dimensions and then in higher. By the way, Gauss-Bonnet is just expectation values of this theorem. So it's very closely related, and curvature is then an average of these indices, and the indices are integers. So Poincare Hopf deals with integers here, while curvature can be, a non-integer. It's an average, an expectation value of indices. So it's a beautiful result, very, very close to the actual theorem which Poincare proved in 1881. Now, my own work on Poincare Hopf started with the Poincare Hopf theorem for gradient fields, where the vector fields are gradient fields. We have a function on an arbitrary graph, and we define then an index at every vertex, and we add up all these indices. We get the Euler characteristic of the number of even-dimensional simplices minus the number of odd-dimensional simplices. So this can be done for graphs. Graphs are closely related. Every graph defines a simplicity complex. And we, of course, understand the Euler characteristic of a graph is the Euler characteristic of its underlying simplicity complex, Whitney complex. We can start now with simplicity complexes, abstract simplicity complexes, which have been defined in 1907 by Max Steen and Paul Hegert. Some famous encyclopedia article. They started from scratch. There's a lot of confusion here, as one has seen. There's lots of, even Euler's theorem was kind of implicitly assumed something about convexity of the polyhedra. Nowadays, these days, we don't, first of all, restrict ourselves to 2 dimensions. We have arbitrary dimensional objects, and this is a very nice fresh start where we have a finite set of sets closed under the operation of taking finite non-empty subsets, which is the simplest geometric axiom system you can imagine. There's one axiom, it has to be closed under the operation of taking finite non-empty subsets. And then we have the vertex sets. These are the zero-dimensional part. It's just the union of all these sets. And what we do is with Poincare Hopf, we just shove the energy which you have, and this energy values is -1 to the dimension, which is for even-dimensional simplices like points or faces, 2-dimensional faces, this is 1, and for odd-dimensional simplices like edges, it's -1. So that's the generalization of these to higher dimensions. So this total energy here, we can now push these energy values to the zero-dimensional part of space. And how can one do that? One has to define a vector field. Every simplex points to one of the vertices, one of the zero-dimensional. If you have that, and then from the zero-dimensional part you go, you have another rule getting back to the simplices. You have actually a dynamical system. You have a discrete vector field flow. And then what we do is we take all these energies and we just move it along to the vertex set. We push it to the vertex set. And of course, this doesn't change the total energy. The total energy is still the same, but now we kind of collect at every vertex what has come in. And we do that, and that's actually just can be expressed again using the Euler characteristic of a subpart of the sphere. And a special case is if you have a digraph which is locally irrotational. Locally irrotational means that in every complete subgraph we don't want any rotation. This is a triangle which produces a rotation. We have seen in Glass Theorem that this produces as an index. In fact, it produces as an index 1 here. We don't want that rotation part. So this is a assumption which is easy to fix. Once we have kind of a simplex which has some rotation, just stellate it at another vertex here and just make it a sink, and then there's no rotation anymore. So we can do that by refining the graph. But what we do is, so if we have that, if we have this D graph, this now defines also a field, right? Because what we can do is in every simplex, because we have no closed loops, we have a total order, and then we have the minimum. We can assign to a simplex the place where we have the minimum given by that order, and then we have the theorem is just now can be expressed in a way which I formulated in 2012, which is just 1 minus the Euler characteristic of the stable part of the sphere. The stable part is the subset of the sphere, unit sphere, which point towards the. And now, how does one derive from this the Glass theorem? So Kate Perkins has shown that, but I'm doing it a little bit differently. So first of all, what we can do is we can take these faces which are not triangles, and we just triangulate it more. But now we have a triangulation. Every face is just a triangle. And then what we do here is we just assign here the orientation. So this, let's just make the orientation just match the next vertex, which is going counterclockwise. So here this has to match that, this has to match that, this has to match this. So this completes also the D graph here. And that's the first thing we are doing. The second thing we are doing is, if you have triangles which produce a closed loop, you see what happens in Glass Theorem. There's also contribution from triangles which have a loop. These are index 1 contributions to the Poincare Hopf theorem. So what we do is we just triangulate it and make it just going out at every point. So that fixes also the, so in this case we don't add, we are sure that there's no triangulation. There's no triangulation in the graph. It's not locally, this is locally irrotational. If it's locally irrotational, then we have the result. And now the indices which we have is kind of, if you look at the definition of the indices, this is really kind of the same thing. Because now what we have is the Euler characteristic of the part which is coming in, which is here. This is coming in and this is coming in. These are 2 points which come in. 2 isolated points that have Euler characteristic 2. 1 minus 2 gives us, 1 minus 2 gives us minus 1. So we have minus 1. So we don't look at number of changes, we just look at the Euler characteristic of the subgraph of that circular graph. For example, in this triangle, we didn't put any triangulation here because what happens is there are 2 changes. If you have R is 2, then we get 0. There was no need to look here at the, this was already taken care of. These triangles don't count. These triangles don't count here, and they also don't count here. We only have indices on the vertices. So that's what I wanted to say today.